Welcome to EFI Advanced Part 22. In this video, we're going to be looking at how to tune using our variable cam feature. We have a lot to learn, so let's get started. Okay, so let's get this video started by talking about how we're going to be tuning our variable cam feature in our engine. Now in EFI Advanced Part 10, we went over how the variable cam concept works, how it functions mechanically, and then we looked at the programming side of things, but we didn't go through the actual process of really going in and looking at how to tune the tables and tune the variable cam feature correctly. Now we know if we change the variable cam or that overlap, that's going to change the exhaust scavenging, change the air mass, and it's going to have a different fuel and ignition requirement when we do the cam angle change. So there's going to be a process to go about really tuning these properly, and we're going to go through that in the next section of this video. So let's jump into that so we can see how it all works. Okay, so the tuning process for our variable cam is going to be pretty straightforward, but we're going to want to use a chassis dyno if at all possible in order to do this process, because we want to build the broadest torque band possible by utilizing this cam advance table, and we're going to have a blend in the table as the cam advance moves around to give us the broadest torque curve possible. And the only real way to do this accurately and precisely is to use a chassis dyno so that we can plot out our torque and we can visually see it change. We might find that one point in the RPM band that has a positive change to cam angle being at a certain point might only have a 5 foot-pound torque increase. And that's something that we may not feel on the road, so it's going to be better off if we have a chassis dyno, if at all possible, to do this. Okay, so now the process is going to be the same regardless of whatever kind of engine you're on. If you're unsure of what the cam advance table is going to look like, so again, if you haven't tuned a variable cam engine and you don't have that composite map built up for the particular combination of parts and the camshafts that are being used, we're going to start off with this process. So we're going to go ahead and zero out the intake cam advance map. Now we're not going to go over in this video doing the exhaust variable cam because it's very specific to the engines and engine management systems that use that. We're going to look at that when we do the system specific training. So in this video, we're just going to assume it has a variable intake camshaft only. So the first process is go in, zero out our intake cam angle table. Now we're going to go in and tune the main fuel and ignition timing tables to associate with this 0 degree cam angle. So we're going to go into our main fuel table. We're going to tune our wide open throttle area and our part throttle areas doing that closed loop or open loop method. And then we're going to go into our ignition timing table, lower the timing down, make our pulls, figure out where the maximum brake torque is, and using the plug reading and NOx sensor data if we have it available, build out those main fuel and spark timing tables. Then we're ready to move on to advancing the cam a bit and seeing the cause and effect. Now, as we rotate the cam, we're expecting that we're going to have increased overlap, increased exhaust scavenging effect, and an increased air mass. And we're going to expect that as we rotate it, it's going to have a higher fuel demand. We're going to have a leaner air fuel if we don't update our fuel table. That's going to show us that we have a positive change as we're moving the variable cam. So if we're tuning on the road and we're not tuning on a chassis dyno, we really can't watch our torque output. One way we know we have a positive movement or positive direction that's gaining us some power is if we move the cam and we see that our fuel table starts to lean out if we haven't updated it. That means that we're getting more air mass and then we're making more torque. So as we change the cam from 0 to something like 10 degrees, we're going to move in small increments. We're going to see that we have our torque output's going to increase, and then we're going to find that we have to update our fuel table. Once we do that and get it back to our desired air fuel, we're going to go into our spark table and we're going to be able to increase our spark timing a bit. Now because we move that overlap, we're going to be dropping our combustion temperature, assuming that we have a positive change in the overlap as we rotate it. We're going to be able to increase the timing 1 to 2 degrees. So my general rule of thumb is every 10 degrees of variable cam movement, we can bump up the ignition timing safely 1 to 2 degrees to see if we get more power. Now we're going to go ahead and increase the timing, do that same process, checking plugs, NOx sensor data, and watching the torque output on our dyno. So once we've done that, now we're ready to go into the next part and increase the variable cam again. So we're going to go from 10 to 20 degrees, and then we're going to do that same thing. We're going to update the fuel table, update our spark table, and see if we have a positive change in torque. And we're going to keep that process going, and we're going to walk it up to right below the maximum rotation of our variable cam control. So typically camshafts will rotate from 0 to 50 degrees or 0 to 40 degrees depending on the engine. Now sometimes we can command a bit more than 50 degrees, and sometimes it might go to 60 degrees. We want to avoid going up that high because as we increase the overlap more and more, we're changing the valve timing events, and we're going to be having typically getting closer and closer for our valves touching each other or having valve to piston contact. So we might have mechanical contact in the engine, which we want to avoid. So we want to limit the range if we're unsure of those clearances. If an engine builder hasn't given us, a definitive variable cam, saying, look, don't go higher than 30 degrees, don't go higher than 40 degrees, and we don't know what that is, err on the side of caution. If the movement is 0 to 50, stay at 40, and therefore you're not going to have contact happen or less likelihood for contact to happen. So once we've done that and we've built out our table, we're going to look at the torque, the differences in the torque as we walked our variable cam up. So we're going to look at the torque curve, and we're going to see very clearly, if we look at the example here, that as we walk our torque, as we walk our variable cam up, our torque is going to increase. It's going to have a positive change as we go up and up. And then we're going to get to a point where we're going to find that we might start going back the other way. We might actually start to lose torque and power as we have too much overlap because the engine isn't going to respond to it. Whether it has a restrictive exhaust or restrictive intake or the combination of both, it's not going to respond and see a positive change. And in fact, when we go up in variable cam, if we have a torque loss, we're going to have a reduction in air mass, and then we're going to see the air fuel start to get rich. So that's another indication, if we're not on a chassis dyno, as we're adding variable cam, if we notice that we start to get rich, we know at that point that the variable cam timing that we're using is not going to work, and we have to back it down a little bit to get the air fuel to lean out to have that air mass increase, and we know we have a positive change at that point. So now that we've done our overlay for our torque band, now we can go in and create a hybrid composite map with the main variable cam timing table. So for example here, if we look at this, the torque plot example with all the torque curves laid over, we can see right here that 30 to 50 degree range was ideal. So we're going to go in and we're going to set up our lower end values from like 2000, and we're going to bring them into right around 40 to 50 degrees as we get up to around 5000 range because it started to peak there. And then we're going to have that 50 degree range, and then we're going to start to come down in our variable cam timing table to match what these torque differences were showing in the different variable cam points. So we're actually going to bring it down to around 30 degrees up top, and we can see that the torque curve actually held better. So we're going to build this composite map. So once we've built that map, we're going to go ahead and do another dyno pool, and we're going to verify that the blend that we just put in the table is going to be sufficient, and it's going to give that nice torque band that we're expecting. And we might find that as we do that composite map that it might not equal that theoretical best of all the torque curves put together. And that might mean that we have to go up or down 5 degrees on this variable cam timing table. So once we've built it, we want to simply add another 5 degrees advance if we're not up to that peak point where we might get contact, or we might want to reduce it 5 degrees. And then we're going to see what the torque curve looks like. So again, we're going to overlay that torque curve, and we're going to see if there's plus or minuses, and then we're going to go ahead and further refine the variable cam timing table. The process is fairly simple, and again, we can see if we have a positive change because our air fuel is going to lean out if we have increased air mass coming in. And again, we're going to increase our ignition timing as we go up in variable cam. It's not uncommon to see something on 0 degrees have something like 20 degrees, and as we get up to 40 to 50 degree variable cam range, we might find that that engine can run at 28, 29 degrees ignition timing, which is substantially higher because we have that decrease in our combustion temperature, and the engine is much less likely to knock. So the power gain is obviously coming from the variable cam and the scavenging effect, but we also can gain a substantial power on a lot of engines by increasing our ignition timing. So don't be afraid to experiment with adding ignition timing in, being reasonable, starting off conservative, and walking your way in, and again, reading plugs and knock sensor data to determine if it actually is knocking or not. Okay, so the other thing I want to cover here in this video is going to be using our variable cam tuning process in a forced induction application. Now, if we have a factory turbocharged engine, it's going to have variable cam timing maps that are going to be set up from the OEM to work with the turbocharger that was fitted to that engine from the OEM. So if we look at something like a Subaru here, we can see that this is going to be a variable intake cam timing table on an AVCS control, which is what they call their variable cam, on the intake. So we're just going to be looking right now at the intake only, not the exhaust on this engine. Let's just assume this is an older STI engine that just had the variable cam on intake only. So looking at the table, we can see that we have load and engine RPM. And if we look very specifically at the table, we can see that the OEM tried to use some of the variable cam to help the turbocharger spool up in the low RPM range to enhance the torque band. And then it rolls off as we go up in our engine RPM. Now with this OEM turbo, we can still go into this table and we can add a bit more cam advance on the bottom end here, and we might find that going from something like 15 degrees to 30 degrees gets the turbo to spool up a bit quicker because we're increasing the exhaust air mass, which is going to spool the turbo quicker, and we might find that we have a broader torque band and a bit more spool range from the turbo. Now the other thing we have to keep in mind is if we have an OEM turbo installed and then we change it to an aftermarket, that aftermarket turbo is going to be laggier, it's going to spool later. So we're going to have to definitely go into this variable cam table and we're going to have to update these variable cam amounts so that we can gain some spool back and the broadest power band possible. So always remember, on a turbocharged engine that's fitted with variable cam, we're going to have to visit this table in our tuning process to find what's going to increase the torque and the spool from the turbo. Now if we have a naturally aspirated engine, as we were tuning in the previous example, and we find that that torque curve or the hybrid blend of the composite map are ideal on a naturally aspirated engine, we might find that 40 or 50 degrees in that mid-range section, and then it tapers off to 20 or 30 up top. It was the ideal variable cam table for that engine naturally aspirated. If we fit it with a turbocharger or a supercharger, we're going to find that that table may have to get revised. Now on a turbocharger, we're going to find that we can't go really high in our cam advance because we're going to have too much exhaust pressure because the turbocharger is going to be acting as a restriction. It's between our exhaust and our muffler, or the exhaust manifold and muffler. So we're going to have to be a bit less on our variable cam. Now typically speaking, 20 to 30 degrees is the sweet spot. If the movement was from 0 to 50 degrees, 20 to 30 degrees is going to be where it makes the best compromise between power and spool. Going any higher will actually lose power. Going lower is just going to lose power and lose spool. So that mid-range point of 25 to 30 degrees is going to be the sweet spot. So if we go ahead the same tuning process on a turbocharged engine, we're going to zero out the table, we're going to tune our main fuel and spark timing tables, walk up our variable cam timing in those 10-degree increments, and then we're going to find where that point is going to actually be, the tipping point where we add some more advance in and then it actually loses power. So the process is going to be the same, but just be prepared that you're not going to see more than 25 to 30 degrees might be the maximum amount of variable cam timing in the table to have a positive change in our torque and our spool from our turbo. And then we're going to go ahead and look at now our supercharged example here. So if we fit a supercharger on the engine and it's a belt-driven centrifugal style supercharger, so more like a Paxton blower, and we put it on our engine, we're going to find that that power band is going to be completely different than a turbocharger, and the supercharger is not going to be influenced from any of the exhaust gas or that exhaust scavenging effect where we have the turbocharger in place, and it might start to back up if we give it too much overlap. We're going to find the turbocharger is going to respond in many cases to increasing the overlap. We might find that it wants more overlap than it did in a naturally aspirated engine. Now in these cases, we're going to be able to go in and absolutely bump up the ignition timing and make more power and take advantage of that scavenging effect. The one thing I'm going to point out here is if we go through the same process where we lower the cam angle down to 0, and then we walk it up from 10 to 20 to 30 to 40 to 50, every time we have a positive change in cam angle, we're going to see our boost actually starts to drop on a supercharger. And that's because we're blowing out the boost between the intake and exhaust. So as we increase the overlap, we're going to have more time available for the boost to essentially blow out of the engine. Now just because we're losing boost pressure as we go up in variable cam timing doesn't mean that we're going to have a loss in power. And in fact, if we look, we're actually going to start gaining power as again we bump up the variable cam timing, and we're going to see that just because we lose boost, that's not a trade-off. We're actually going to gain a lot more power with this variable cam timing tuning. So don't worry about that. If you see it, don't be alarmed. So your first pull on 0 degrees might be something like 10 psi, and then by the time you're done tuning the variable cam out, you might only be at 7 psi or 8 psi. So don't be alarmed. That's not something that's going to be a concern. We're going to notice that we gain a drastic jump in power, even losing the 2 or 3 pounds of boost.